All right, so now we're going to talk about a few important special cases, the first of which is the case of lower triangular matrices. Okay, so the definition is as follows. So the n by n matrix A is lower triangular if it can be written as follows. So basically, what is happening is that all the entries above the diagonal are 0, okay? And sometimes I will denote this in the following way. You have a matrix and you just have a triangle which is shaded in. Those are sort of the non-zero, possibly non-zero entries, and then these are 0 entries. Okay, so in any case, so the theorem is as follows, that if A is a n by n lower triangular matrix, then it is invertible if and only if AII, which are the basically entries in the diagonal, are all non-zero. So that means that the entries on the diagonal are all non-zero. And then if you know something about determinants of matrices, it's like then you can figure this out based on the fact that the determinant of a lower triangular matrix is just a product of the diagonal entries. Okay. All right. Anyway, so in any case, the reason why the special case of lower triangular matrices is of interest is because it's very, very easy to solve for a linear system of equations when that coefficient matrix is lower triangular. Okay, and let's see why that's the case. You can sort of see it by just writing down what happens, what the system of equations looks like. It's like corresponding to ax is equal to b. So if you have ax is equal to b, and A is lower triangular, then what happens is that the equations look like the following. So A11x1 is equal to b1, that's the first equation. Then A21x1 plus A22x2 is equal to b2. And then eventually AN1x1, ANNxn is equal to bn. Okay, so the way you sort of see this is that if you look at the first equation, you can there's only one unknown in the first equation, which is x1, and you can solve x1 by dividing b1 by a11. So x1 is b1 divided by a1. Okay, so once you know x1, then you look at the second equation. Then the only thing you don't know in the second equation is x2, because you already know x1 from the previous thing. Okay, so now x2 is b2 minus a21x1 divided by a22. Okay, and you can sort of keep doing that, right? So xn is going to be bn minus the sum of an1x or ani xi. I goes from 1 to n minus 1. Right, these are all the entries up to the n minus 1 term divided by a n n. Okay, so again, it's like this is what is going to be called forward substitution, because you solve for x1, you substitute that to the next line. x1 is obtained from this, you know x1. You can then use it to solve for x2. Then the next equation will involve x1, x2, and x3. You know x1 and x2, so you need to solve for x3. So eventually, you know, by solving, it's like for each of the unknowns in sequence, it's like you can very easily solve the system of linear equations. Right, so let me sort of write down the algorithm for this. And as I said, it's like this approach, it's called forward substitution. So of course, you know, if you look at this construction, you'll see that in order for this to work, A has to be invertible, because there's this one-to-one correspondence between A being invertible and all the diagonal entries being non-zero, right? So you need to have that all these diagonal entries are non-zero because you're dividing by the diagonal entries. Okay, and then conversely, if all the diagonal entries are non-zero, this construction gives you the solution, and so A is invertible, right? So there's that's why it's an if and only if statement. Anyway, let me try to write down algorithmically what this is, right? So x1 is b1 divided by a1. We have that, a11, sorry. Yeah, a11 here. Okay, and then so for I equals to 2 to n, you do the following. Then I need to sort of compute this sum, all right? So I'm going to store the entries in the sum. It's like in this temp variable, so temp is equal to 0, and then for k equals to 1 to I minus 1, temp is equal to temp plus aik times xk, right? So those are the entries in this sum here. Then you end that. Okay, so temp now contains essentially all the entries in a particular row except for the one involving the unknown which you don't yet know, right? Okay, so xi is equal to vi minus temp divided by aii, and then you end the for loop. Okay, so that's all there is to it. Very, very straightforward algorithm. You can also write this in a vectorized form. So many times when you have these for loops, it's oftentimes possible to, especially when the for loops are just doing essentially these kind of component-wise products, it's oftentimes possible to do what is called vectorization. So MATLAB was designed to work with matrices and vectors, all right? And so instead of using for loops for these kind of calculations, I mean, it's like you can sort of see that what is happening basically is you're computing something like a dot product between two vectors, and where one of the vectors is really sort of a particular segment of the matrix A. Okay, so if you can extract that part of the matrix A out and think of it as a vector, then you can do the dot product of two vectors in order to replace this for loop. Okay, so if anyone's interested, I can talk about that offline. But you know, that's just again a heads up. It's like if you might want to search out for this idea of vectorization of MATLAB code that has the potential to dramatically speed up your computation if you're going to use MATLAB in a more serious fashion. Okay, anyway, so I won't go too much into details, but you know, this is sort of the minimal way of implementing this. And so that was the case for lower triangular matrices. The other case, which is very closely related, is that of upper triangular matrices. Okay, so let's look at upper triangular matrices. And as the name implies, what's happening is that now all the entries below the diagonal vanish, right? Right. A is upper triangular. If you can write A as A11 to A1n, A22 to A2n, ANN. Then these entries below the diagonal are 0, and sometimes I would denote this by just drawing a triangle, like this, and then shading this in, and then it's understood that these entries are all non-zero. And again, this is invertible if and only if all the diagonal entries are non-zero. So invertible. Okay. All right. So as before, we can try to write down sort of what the linear system of equations for a upper triangular matrix would look like, right? So you'll have A11 x1 all the way up to A1n xn equals to B1, right? All the way down to ANN xn is equal to Bn, A n minus 1 n minus 1 xn minus 1 plus A n minus 1 n xn is equal to B n minus 1. All right, so so you can do sort of that kind of substitution trick, but now you have to start from the bottom and go upwards, right? So you know that xn is equal to bn divided by ann, and you know xn minus 1 is equal to bn minus 1 minus a n minus 1 n minus 1 b n minus 1 n times xn, okay, divided by a n minus 1 n minus 1 and so on. So this is, as you might expect, another substitution method, but it's called backward substitution. Okay. All right. So you sort of keep going up and substituting backwards, right? So let me just state, let me just write down the algorithm for you as before. Okay, so the algorithm is as follows. And conceptually it's very similar, except that you have to be careful with the indexing. The indexing is, I mean, again, not too difficult to figure out, but you just have to be careful. So backward substitution. Okay, so xnn is equal to bn divided by ann. And then for I equals to 2 to n, you do the following. J is equal to n plus 1 minus I. Your temp is equal to 0. And then you'll go from k equals 1 to I minus 1. And then temp is equal to temp plus a j comma n plus 1 minus k multiplied by x n plus 1 minus k. And then you do the end, and then xj is equal to bj minus temp divided by ajj, and then you end the for loop. Okay, right. So I should mention that in MATLAB there's the possibility of switching the indices. So instead of from 1 to n, for example, you can go from n to 1, or whatever you choose. All right, so that's something you want to look up in the MATLAB syntax, and that would sort of avoid having to switch between this k and j indices. All right. sorry, not, so that would avoid having to write this index as n plus 1 minus k. You could sort of switch the ordering of that k index. Anyhow, so there's a way to sort of write it. It's like a little bit more in a more readable fashion. It's like in MATLAB, by using the fact that MATLAB allows you to do for loops. It's like from a larger number to a smaller number, for example. Okay, so anyhow, it's like so that's the basic setup for both forward and backward substitution, which is relevant for lower triangular and upper triangular matrices. Okay, and then the next thing we're going to do is going to discuss Gaussian elimination, which is a way to factorize a matrix into the product of a lower triangular and upper triangular matrix. And then once you've done that, you can use the forward and backward substitutions in order to then solve the linear system of equations. So let me just stop here for now.